Welcome back. In today's video, we have a quick overview of the inverting amplifier. In the next series of videos, we'll tackle problems that uses the inverting amplifier and may include non-inverting, because we have already been through the non-inverting amplifier and a series of problems, so that link will be in the top right. So in our case, the inverting configuration is formed by grounding the V plus terminal of the op amp, and if we ground that, we can then apply the signal into R1. So in our case, our voltage signal into R1, the non-inverting had the signal applied into the positive, and then we ground the R1 resistor. In this case, the voltage signal applied to R1, then we ground the V positive. And the R2 resistor, which connects V out to V minus, in this case, connects V out to V minus, provides the negative feedback for our inverting amplifier. So it is important to know that if a positive voltage is applied at V in, the V minus terminal, in our case, the V minus terminal will rise in voltage, forcing V out to become negative. So this is in essence that inverting amplifier. So if it's positive, V out becomes negative. So we can then go ahead and determine our gain. So we can first determine V out, and then we can determine our gain for the amplifier. So first thing we look at is that we can use superposition, or we could use node voltage method. And superposition is simpler, so let's go with superposition. So with superposition, V minus 1 is equal to, so in this case, let's do that by, let's set V out equals 0. So if I set V out equal to 0, I would then get the voltage across R2 with reference to V in. So that would be the voltage across R2 by voltage division with reference to V in. Then V out 2, V minus 2 is equal to, set V in to 0, take the voltage across R1 with reference to V out, and that will be V out R1 plus R2. Then by superposition, we can add both of those together. So V minus 1 plus V minus 2 is equal to V minus. So V minus is equal to V in R2 all over R2 plus R1 plus V out R1 all over R1 plus R2. We can then go in terms of, so to get V out in this case, we then go and say, okay, we have virtual short. These op amp with the feedback element operate in the linear region, so thus we have an ideal. And in this case, if it's ideal, then we have virtual short, and by way of virtual short, we can thus say that we can apply the same voltage at V plus to the terminal V minus, and we know V plus is equal to 0, so we then have that V minus is equal to 0. By V minus equaling to 0, we can then say that V minus is equal to 0. If we times both sides of the equation by R2 plus R1, those cancel out. We move V out to the left. Then this becomes negative R2 all over R1 times V in. And that is our output voltage. We can then go ahead and state that our voltage gain is V out divided by V in, and thus we have that our voltage gain for our amplifier is negative R2 divided by R1. So there we have it for our output voltage and our voltage gain. So the quantity negative R2 over R1, as we mentioned earlier, is our gain. So it is our closed loop voltage gain, and it's both. So it's the closed loop voltage gain, both for negative and positive V in. Also, we should take a look at, in this case, when V in is positive and V out is negative, current will flow from V in through R1 and R2 and into the output terminal of the op amp. And we know that current flows from positive to negative, current convention. We can thus say that if V in is positive, V out is negative, then we have a current flowing this way. And if there was a load element, it would flow to, and we'll assume that there's always a load element. So if the current is flowing from the positive, it will then ultimately to the negative supply, so it will then flow to the negative supply. So therefore we'll get something looking like this. No current flows here. And if the, conversely, I could say when V in is negative and V out is positive, current will flow from the op amp output terminal through R1 and R2 and into the V in source. However, because it's flowing from positive to negative, it has to originate from V plus, well, the positive voltage supply. So then we get something looking like this. And there we have it. So we can then go ahead and look at the input resistance. We know that the input resistance for a non-inverting amplifier was infinity. But before we can put that on the screen, but let's talk about the input resistance for the inverting amplifier. So the input resistance, as you know, is defined as the ratio of V in to I in. So where V in is applied, V in is the applied voltage signal, and I in is the current drawn from that source by the op amp circuit. So in this case, we can then put I in, and then to get the ratio, or we have to find I in first. So we know that I in is equal to the voltage. So we can then say the voltage across the R1 resistor divided by R1. So that is V in minus V minus divided by R1. There we have the current. We know by virtual short that V minus is equal to 0. So thus this simplifies to V in all over R1. Thus, by, in this case, Ohm's law, we can then say that V divided by R, the V divided by I is equal to R. So our R Thevenin, which is in our case our input resistance, so our R Thevenin is equal to V, which is V in divided by I in. I in we know to be V in divided by R1, so thus this is equal to R1. So our input resistance, I can call it R in or R Thevenin, is equal to R1, which we see is finite. So as I was saying earlier, that the input resistance of the non-inverting amplifier is kind of one of the circuit principal advantages, because in the non-inverting, as you can see that the inverting amplifier configuration can draw current from the source, but in the non-inverting amplifier, it prevents, so the resistor being the R in being infinity prevents the circuit from drawing current from the signal source, our input signal source. So we know that in a non-inverting, as always, the current into the V negative and V positive is equal to 0. So if we then say that R in for a non-inverting is equal to V in divided by I in, we can then say I in approaches 0, and this is equal to infinity. So for a non-invert amplifier, we know that R in is equal to infinity, and that stopped the circuit from drawing current from the source. And as we know, the inverting does not prevent that because the input resistance is finite. So basically, that's it for the inverting amplifier. Next, we'll post some video on this specific configuration, and some of these problems we might have to draw from the what should I call it, the non-inverting. So here's the list of non-inverting problems and so forth. And basically, let's get into some problem. So see you next video. Bye.